Okay, let's get started. So in the assignments on Blackboard, I posted the take-home quiz. I was trying to print out copies for you to give you, but the printer failed. So you'll have to print out your own copy, and don't start trying to do these on that and keep erasing until you have your final draft. But do work on other paper and then create a final draft on your printout, and you'll turn that in Monday in class. Okay, that's quiz 9. So you can use any resources you like, but the ground rule is you can't consult any other person. You can't consult a friend, a parent, a child, another teacher. But if you want to email me for clarification, you can email me as much as you want. Okay, just you got to work on it by yourself. But then you can use any resources, online, book, whatever, class notes, videos. Okay, print out a copy, the link above, which will write your final draft. Submit Monday in class. All right, and then I just want you to just think a little bit about the new material. So it just be something light and easy that I'll post. It might be my math lab, or it might be just a couple exercises, so that B will not be heavy and long. Okay, so the real focus is the take-home quiz, that's all material that's on your exam next Thursday. So we have an exam a week from tomorrow, exam 3. So I opened up. I thought I did. Just got to move it up. It's in the wrong place. Sorry, we'll move it up to the top here. Okay, so now in the quiz and exam, first folder, exam 3 and related quizzes. So I got review outline, like previous exams. Nothing's on the exam that's not mentioned in that review outline, okay? That's a full and complete review outline. It should be the centerpiece. Whenever you're studying, you have that in front of you, and you're relating everything you're doing to something on that sheet, okay? And then I've got the blanks and solution versions of 6, 7, and 8, okay? So I can't underscore enough the importance of the quizzes, because whenever I put a quiz together, I'm trying to assess the most important things. I'm always trying to assess the very most important things when I write a quiz. Okay, so quizzes 6 through 9, so 6 through 8 are here, and then the take-home quiz. Those are the 4 quizzes that are most of the exam. There are some things that didn't get covered on a quiz, but at least 75 or 80% of the exam material will be from those 4 quizzes. Arguably, quiz 7 may be the most important quiz of all the whole semester, okay? Because it's all about the meanings of the notation, and we're looking at rates and accumulation all together, okay? So arguably, quiz 7 could be the most important. Lucky 7, right? Lucky number 7. So you might keep that in mind. Really important questions. If a student did well on that quiz by the end of this course and didn't do well on anything else, I would be happy. Okay? Somewhat. All right. Okay. I'd be happier than compared to any other quiz. Questions on exam 3, which is next Thursday. And then after you turn in quiz 9, I'll put the full solutions up for quiz 9.
Should we be looking at our homeworks?
Sure. Yeah, so the review outline is definitely important, quizzes, and then beyond that, homework and videos. We're all, yeah. Now, on that review outline, I've I've highlighted certain classes and left some classes out. So I think I've left 3 classes out by highlighting which classes pertain to which bullets. I tried to see, because we had the mastery exam, this goes way back to mid-October now. So the material that's covered goes way back. So you're really going to have to start your studying early. That was over like a month and a half ago now, because we had the mastery exam in there. So starting October 16th, and so because of that, I tried to whittle it down and kind of, there's at least three lectures that are not in this list to help you a little bit narrow down your studying. So that's the review outline.
That's just at the math testing center?
Same procedure as all the other exams, and that'll be Thursday. Questions on the exam? And then again, in assignments, you have your take-home quiz, which is quiz number 9, just like, and it's 3 pages. So make sure that you print out all 3 pages. Okay? Yes, sir?
For recitation on Tuesday,
Yeah.
are we just gonna go over stuff? Like for the exam on
No, new material and recitation.
Tuesday?
Yeah, so the optimization problems is the last thing covered on the exam. So this problems you're turning in today, that's the last material. So what we've done since optimization will be very, very important for the final, but will not be on the 3rd exam. In fact, what we've done since optimization now, this is kind of the pinnacle of the course, right? We're seeing how everything is coming together, right? So this is why we've made this journey, is for this last week is the whole reason for the journey. So that will be very important for the final, okay? But it won't be on exam 3. So I don't know where I was going with that, but what was your question, Kevin? Oh, so Tuesday, recitation Tuesday and Thursday, one more, it will be new material. It will be similar to, if Mercibel agrees, she'll have another teaching experience like you did the last time. Okay. Any questions about logistics, assignment, or exam? Start studying for the exam soon. Don't wait till Tuesday or Wednesday. Because, like I said, it goes all the way back to material in mid-October. Okay. So, let's kind of review where we were. So, we were looking at, what was our trying to find? We're trying to find now closed form accumulation functions. We spent the whole first month and a half building up our accumulation function, but it was open form. It was the open form, the integral form. Okay? Now that we've gone through this, all the finding the closed form rate functions, now we can talk about finding closed form accumulation functions from rate. So let's do this. So here's accumulation function sine 3x. What is the rate function? Alina. Cosine 3x times 3. So now I want you to write me, for that rate of change function, starting at x equals 0, I want you to write me the open form accumulation function for that rate, beginning accumulating at x equals 0, and then the closed form. So this is a review from last time just to get our reoriented. Open form and closed form of the rate of change starting at x equals 0. X equals 0. Chloe, you're not writing, so that means you know it. Yeah, tell me the open form.
It's going to be the integral
Okay.
from 0 to x
Okay.
of 3 cosine 3t dt.
She nailed it. Oh, but I didn't. Let's see here. Okay, hold on a sec. We interrupt this important. Okay, let's try this again. All right. Okay, now you can open your eyes. Okay, very good. 0 to x, 3 cosine 3t dt. Okay? What's that?
Where does the t come from? Because the variable above is using the
Yeah, so we've talked about this several times. So we stop accumulating at x.
okay.
So we can't use x to mean all the x values along the way because x is where we stop accumulating. So we need a different parameter to represent all the x values from 0 to x. And if we put x in there, then we're only going to get the rate at the end. We're not going to get all the rates in between. You see? Okay, cool. How about the closed form? Ariana? Get the closed form? Remember?
Should be f of x.
Uh-huh.
Because that's sine 3x minus
Right. So we can start this way. Make it easier on ourselves. F of x minus f of 0. And we know what this means, right? If we have the rate function, we have rate functions over here on the left, and we had accumulation functions on the right, and we said, what are two different ways that we could talk about the accumulation from a starting point up till x, right? We could add all the bits of change. K delta x plus k delta x. Or if we have the accumulation function, we can just take the final accumulation minus the initial accumulation. And that's where that comes from, right? That's where that comes from. And so, right, 3 cosine 3x minus 3 cosine 0. Question?
Yes, I thought it was the f of x that was pretty good.
Yeah. Wow. It was late when I did this.
Wait, oh.
That's not right. If you put that,
Wait, the first one. What's the first one?
okay, so what is f of x?
Sine 3.
Sine 3x minus,
Sine 0.
are we good? Okay, so the example we ended up last time on was this one. We had the f and we took some time to find that rate, and we simplified that rate function to not minus x e to the minus x squared. Okay, so once again, practice. So the open form accumulation starting at -2 and the closed form accumulation starting at -2. What's the open form accumulation? Starting at -2 and the closed form starting at -2. Okay, Tiki, how about open form? What's the open form? Accumulation for this one. Can you just do it by looking up there instead of reading your notes? Integral?
Yeah, integral.
Okay.
Integral from x to 0.
Okay, we're starting at -2 now.
Negative 2 to 0. 0 to negative 2. Negative 2 to x.
-2 to x
Yeah.
of f or of the rate? So we're going to integrate this one or this one? The f or the rate?
The second one.
This is the rate.
Yeah.
Okay? Okay, so that is what she said was -2 to x of our rate. dt.
T.
Wow. Sorry, guys. I'm glad you guys know it. Good? And then open form, or closed form. Closed form of the accumulation function. Ryan, want to try that?
Would be square root of e to the negative x squared minus the square root of e to the negative 2 squared.
How do you do? Okay. So, go ahead.
I just have a question. So the closed form,
Uh-huh.
like I know those are equal, but like, is that how you would solve the open form? Is by going to the closed form?
Open form shows the process, and closed form allows us to generate outputs quickly. So it's a standard function that allows us to generate. I think we're getting to where you're thinking. So we're not there yet. Okay, but for now, so we know that open form shows process, Closed form is a standard function that generates outputs quickly. In this case, amounts of accumulation starting from -2, right? So plug in an x, it'll give you how much is accumulated since -2 up to x, whatever x you plug in. Are we good? So that's review. So we left off on this graph here, and I've got that open form. I've got the open form graphed, and then we said let's write out the closed form, and we could check it by seeing if the graphs are the same, right? So this is our open form that we just wrote, is that right? And then is this what Ryan just said? So if I make it black, it should make that graph black, and it does. Okay, so then we ask the question, what's the result of starting accumulating at -2? So looking at the graph, how does that relate to the graph if we start accumulating at -2?
This is 0.
What's that?
This is 0.
And why does that make sense that the amount of accumulation would be 0 at -2? Yeah, Christian?
Because that's our starting point, so it's like our A, so everything's accumulating off of that.
Right, so if we choose x to be -2, how much has accumulated?
0.
0, because that's our starting point, so nothing's accumulated. So if we choose -2, we should get 0. And so then we said, well, what if we started accumulating at -1? So in other words, we want to look at this graph. Right? So that's the open form, -1 to x of RT dt. So if I were to graph that, what will we see? So what can you say about what we'll see if we start accumulating from -1 instead of -2?
0, 1,
Is that-
-1.
He says 0, -1.
I thought it would just be, cut off everything before -1 and stay the same functions each. You plug in
So it's just going to remove some of the graph.
Yeah, because if you plug in -1, it's still going to be the same answer. You're not changing the function.
But if we start accumulating from -1, now,
I just think the graph will shift. So starting at -2, or the 0 would be a -2, the 0 would be a -1.
so the 0 is going to be a -1,
That's what I mean.
right? And so are you imagining this for the new graph? So that's not, I'm not graphing the open form, I'm just graphing your conjecture. I'm just graphing your conjecture. James doesn't like it.
No, because of the square and square root, your problem is going to condense.
Oh, so, okay, so you're saying that the whole thing is just gonna kind of,
Yeah, instead of going from -2 to 2, it's probably going to go from -1 to 1.
okay, all right. So that's I don't have a way to show that, but that's another theory. Okay, Brian.
Want to shift down.
He wants it to shift down. Why? So what's wrong with this shift? So you think it'll shift down, but you're not sure why. Good.
So it's gonna keep accumulating forward. Changes where it stops accumulating and shifts to right.
Okay, other ideas? So we've got that it's going to condense in so that there's this, if the whole thing's going to squeeze in, we've got that it's going to shift to the right, and then he says the first one's going to shift down. I'm sorry that you're not.
No, it's not that. You're just really excited.
Christian.
I thought it was just going to be a negative, like it was just going to start at like the 1 would be a 0, but everything else like up until the 2 would be like a negative number.
So how would we adjust the first graph to get what you're thinking?
I think like make it a little wider.
But then how will you get a root at -1? Don't we know we're going to get that root at -1?
Oh, I mean like just like this, so it'll come in kind of wider. You know
And then wider. I don't.
what I mean?
All right, let's kind of focus our attention here. Look at the two open form rate functions. What's the same of accumulation functions? So from -2 to x RT dt and -1 to x RT dt. Okay. What's the same about both of those? Though they have something in common. So what do those two accumulation functions have in common?
The rate's the same.
They have the exact same rate function. So how about this? Do these two functions have the same rate function? So at, say, -2. And let's do, say at -5, -1.5. Do these two graphs have the same rate? How do we see the rate of change in the graph? And do these two at -1.5
Changes in y over changes in x.
changes in y over change in x, right? So for a small change in x, we look at the relative size of the change in y. Are the rates the same?
If they're the same, it's probably easier to draw.
Exactly. Okay. What about at 0? What would you say the rate is right there at 0?
Well, that's, isn't that not the same now because of the fact that you shifted the graph, like,
At x equals 0
The rate should still be the same at the
what's the rate of this? What would you estimate it to be? 1.5, 2, or scales, or we'd have to adjust for the scale, but some positive value. What's the rate of change here?
0.
0. Are the rates of these two the same? So, then does it make sense that all accumulation functions of this rate function are going to have the same rate of change function? Yes. So any accumulation function that we do of this rate function is going to have the same rate function, right? This accumulation function and this one is built on the same rate.
no, but you're shifting.
No, you shifted it.
Oh, yeah.
That was your conjecture.
Well, yeah, but,
This is just your conjecture. I did not graph this. I have not revealed it yet. All I did was shift it to what I suspected would be what most of you thought.
well,
I
I
thought
know
you
what
were-
he says now.
Yeah, I thought you were showing us that. I thought you were saying that it was.
This is your conjecture.
It's wrong.
So,
Wait, I'm still unclear.
Your conjecture of this.
well, then wouldn't the graph compress then?
What's that? And how about so now we're saying, what about your conjecture?
It's wrong.
It's not right because both these accumulation functions have the same rate. Okay? They both have the same rate, and clearly these have different rate profiles. Here, the rate of change of our original is much greater than the rate of change of the new one, and here, the rate of change of the old one is 0, and the rate of change of the new one is clearly a positive value. So we need to revise our conjecture. So what we want this thing to have, this 0 at -1, but have the same rate profile, exact same rate profile as this function. So
Can you just shrink it so that the top of the parabola is just lower, but it's still the same exact shape and starting at 1 and ending at -1 and ending at, sorry, I messed that up. Starting at -1 and ending at 1. Just shrink it
shrink it horizontally.
And for
in every way possible.
and just do one without the other.
Yeah, scale.
Like scale it down.
It won't keep the same rate profile.
I can see why.
It won't, it's a because you'll have all the same rates, but now they'll be at x values that are further in.
Oh,
The whole thing will be smaller. You're right, but now you have all the same rates, but they won't be at the same x values. So we need all the same rates at the same x values. Jeanette?
Oh, don't you just shift it down to the,
Okay, so this is what Brian said. So go ahead, explain.
because, like, the f(x) is still the same function, you're just taking the rate of it, so you should just basically start it.
What's that?
That's the right answer.
You tell me?
Or was that hard?
Yes, that was the right answer.
Austin, so why is it right?
If you shift it down, it keeps all the same rates as the original.
Right.
The 2.
Right?
Or the -2.
And also?
0. And it keeps the zeros at -1.
0 at -1. Okay, so watch. Now I'm going to make this A and we're going to do a slider. So if I change this to A and make A equal a slider, say from we're -2 So what's going to happen when I change the slider, or in other words, change the starting point of accumulation?
Shift up.
Pushing the curve.
What's it going to do?
Shift it from the curve or
It's going to shift it down. So if I put it at, if A is negative 0.48, it's going to have the same rate, it's the same rate profile, but now it starts at negative 0.48, accumulating. What about A equals 0? Yeah. So it's now it's going to accumulate, so I'm going to turn the rate on. The rate is red for rate, okay? So now it's just going to start accumulating at this rate. What rate is it? 0. And if we're back at, say, negative 0.8, what rate is it going to start accumulating at negative 8? Whatever that rate is right there. Okay, so let's go back to negative 1. Write the open form for the accumulation starting at negative 1. Let's compare the open forms. Somebody new. What's the open form?
This is starting at -1, right?
Yeah, sorry, never mind. Kaylee, you want to do that one? Open form?
Um,
I'm sorry, closed form. Closed form.
let's see. Closed. For the
For this open form accumulation, now we want to write the closed form.
it would be square root of e to the x squared
Uh-huh.
minus e to the negative 1 squared.
That's right. It's going to be just like this one, but now this will be
2.
So now compare these two. How do those graphs compare? Or those equations, and therefore how those graphs relate to one another, looking at the closed forms. So it's the same. How can we see the same thing we just saw by looking at the closed forms? Is what I'm asking.
I have a separate question.
Okay, so let's answer this one first, and we'll go back to your question. So how can that same fact that we just saw be seen in these closed forms? Yeah, Steve.
It's just gonna have a different y-intercept, right?
Okay.
So shift it down, like the exact same thing,
Right. So we have the function, the expression of x is the same, and then what does minus a constant do?
Shift it down.
Shifts it down, and so now this is just minus a different constant. You see? So that you see it in the closed forms that these accumulation functions are just different by a vertical shift, and that vertical shift then gives us a root at the starting point of accumulation. So the red is the rate, and then I'm showing both. This is starting at -2, and then accumulating at -1. They both have that red rate function, and they start accumulating at the x value, or accumulation is 0 at our starting point of accumulation. Okay, really important result. Does this make sense? What's going on? Okay, Melody, what's your question?
I don't understand how, or you say it starts at accumulating at -1. Does everything before -1 not count as accumulation?
So we never talked about this, but you can accumulate backwards. We could accumulate from -1 to -4.
So it's like breaking down.
So it's like going in reverse. It's like accumulating in reverse. So or you can think of this as everything is accumulated up to -1, and now.
I just don't understand.
What's that?
I just don't understand the vocabulary.
Yeah, it's a good question. So really, when this really shows the graph of accumulating starting at -infinity. Okay, which is positive accumulation starting from -1 going to the right, and reverse accumulation starting from -1 going that way. And so that's why it's showing both. Does that help?
So would that always be the same even if it's below the x-axis? Or is there no way to tell just by
Well, it doesn't, it's depending on their rate and the accumulation, it doesn't have to be negative and positive. It can come like that down this and do this, it can come like this, it can go through. So there's nothing, the fact that it's a negative amount of the quantity before and a positive amount after is just a function of which rate we started with. Does that make sense? So that, yeah, so it could, for a different rate function, the accumulation function might do this. It might do this. It might do this. It could do a whole mess of things.
So y has to equal 0 at that point.
But y equals 0 at this quote-unquote starting point of accumulation. Zoe, did you have a question?
That was my question.
Yeah. Right. Okay. Other questions? All right, so given a rate function, how many accumulation functions does it have? Many, right? So many depending on where we pick the starting point of accumulating, right? So given a rate function, there's many. Go back to A here. So given a rate function, that red rate function has all these accumulation functions and more. So these are just the ones that I showed in the range of A. Okay. Given an accumulation function, how many rate functions does it have? There's only one rate profile given an accumulation profile. Okay. So let's. Here's a new term, antiderivative. Suppose that f and g are functions. So we call g is the derivative of f if g is f's rate of change function. Review, right? We've been talking about that for 2 months now. G is the derivative of f, or no, if g is the rate of change function. And so if g is the derivative of f, then f is the antiderivative of g.
Is that like an integral?
Okay, we're getting there. We're getting there. So if g is the derivative of f, if g is f's rate of change function, then f is called an antiderivative of g. So here's a visual of that. If we take the derivative of f, we get the rate of change function. So now, an antiderivative of the rate of change function then is the accumulation function. That's right. And how many are there? If you start with the rate of change function, how many antiderivatives does it have? Many, right? Many. All the vertical shifts of some of the accumulation profile, right?
So we have one rate of change that has infinite accumulation.
Yeah. Or many. Many accumulation functions that all have the same rate. Like the two we looked at, we're starting at -2, starting at -1. Those both had the exact same rate. They came from the same rate function. We built those from the same rate function. Okay, so every accumulation function is an antiderivative of its rate of change function. But like we said, every rate of change function has more than one antiderivative or more than one accumulation function. Okay, we good? So every rate of change function has more than one antiderivative. So here's a rate of change function for x cubed. So I want you to write me the closed form version of this. This is accumulation function, right? It's the accumulation of this starting at x equals 1. Accumulation at this rate starting at 1. Write me the closed form accumulation function. Go.
Isn't that supposed to be opposite?
What?
Isn't the rate of change supposed to be with the input, or is that like a different question?
This shouldn't. That notation should be perfectly clear and consistent with what we've done.
Yeah, actually, I was messing up
Okay.
with TMS.
Yeah, this I'm giving you the rate.
Yeah.
Okay, so there's something slightly different here. Something slightly different. Molly, what's different?
The original function could be a lot of things. It could be x to the fourth plus 1, x to the fourth plus 2.
Okay.
Constantly add constants, which would be 0 equals 0.
Okay, so what's different about this problem than the ones I gave you before?
There's a lot of antiderivatives.
What's that?
There's a lot of antiderivatives. There's not
Um,
a lot of
okay.
constants.
What, so, Brian,
You didn't give us a function to use.
I didn't give you the accumulation. Now I'm just giving you the rate. I didn't give you the accumulation function from which that rate came. All right, and so can we figure it out? So we're asking ourselves, what function has this as its derivative? So this is an easy, hopefully an easy one. Chloe.
It's gonna be x to the fourth plus possibly some constant.
No, but you did this before. You did that.
Well, the x to the fourth.
Well, I want the for this starting at 1 and accumulating to x. What's the closed form accumulation function?
F of x minus f.
Okay, f of x minus f of 1. Good. And so I didn't give you this time. I didn't give you f of x, right? So what is that? So f is the antiderivative of 4x cubed.
X to the power 4
Just x to the power 4.
plus whatever constant.
No, so you guys. I want someone who has never had calculus before. Ross.
It's x to the fourth minus
What's that? Well, where do you get the minus 1?
1 to the fourth.
Okay, so first we have to say what function has this as its derivative, or in other words, what's an antiderivative of this? And you thought, oh, did you think x to the fourth, Ross?
Yes.
Yeah. And so now we've done this before, so it's going to be. Oh, good. F of x minus f of 1. And Ross, you said it was?
X to the fourth minus 1.
X to the fourth minus 1 to the fourth. Okay, what about this? Negative 5 to x. Aaron.
X to the fourth minus 5 to the fourth.
What to the fourth?
Negative 5.
Negative 5. And what did we say? We said all these accumulation functions given the same rate, how did their graphs compare?
Shifted on the y-axis.
A shift, right? And so by adding or subtracting a constant, we just get a shift, right? We get a shift. So we're getting different shifts of the same antiderivative or accumulation. Okay? This one. Kaylin.
Pi, x to the fourth minus pi to the fourth.
Minus pi to the fourth. Okay? So these are all antiderivatives And that's what, so you of 4x cubed. All of those are antiderivatives of 4x cubed. How can we check? So if these are all antiderivatives of 4x cubed, how can we check to show that that's right? What's that? And how do we find the rate? Given that, how do we find the rate of change? Yeah, take the derivative. Is that, Danny, is that what you're going to say? Yeah, so Danny, what's the derivative of x to the fourth minus 1 to the fourth? 4x cubed minus 0. What's the derivative of x to the fourth minus negative 5 to the fourth? Shannon? 4x cubed minus 0. These all have a derivative of 4x cubed. And because they all have a derivative of 4x cubed, they're all antiderivatives of 4x cubed.
Is there any way to find the only ones?
There are many. There isn't only one. That's the whole point. There are many. There are many. Okay, and so when you don't put these bounds on your integral sign, we call that an improper integral. That represents all the antiderivatives of 4x cubed. Represents all the antiderivatives of 4x cubed. Okay, so x to the fourth minus a to the fourth.
Assuming that the improper integral, the one that you have there, is 4t cubed dt.
What's that?
It would be 4t cubed dt, right? Not 4x cubed.
No. So this is fine because there's no conflict. It's when there's a conflict,
Okay.
right? So now this is okay. So now we're just letting x be how we go from point A on. All right? Yeah, the problem is when we have that upper bound and those are the same. Yeah, that's the problem. Okay, so, yeah, question?
Do we know for sure that f of x is x to the fourth? Like as a fact, just from the rate?
No. I could have, so any antiderivative we could have started with.
Okay.
So we could have started with, it's just the easiest one, just without a constant. But had we added a constant, then it would have been there and subtracted away. And there and subtracted away. Yeah, Melody.
On the final exam, are you going to do, if you will, more complex versions of the same one or just the same?
I will prepare you fully for the final exam. Okay, we're getting there. Okay, so yeah, that's where we're going. You're just jumping at. Okay, so x to the fourth minus a to the fourth. Well, minus a to the fourth is just a constant. Okay, so we can also represent that as plus c. So here's a sum rate. If the improper integral are all antiderivatives of some rate function dx is f of x minus f of a, which we kind of write as, or we can also write as f of x plus c. So what does c equal? What does c equal?
That's a shift, right?
It's a constant.
What constant is it?
Any constant.
No, that's not where you start accumulating from.
Yeah, but what is its value?
Zero?
No.
I think we
The
should.
accumulation at the starting point.
All of that.
What does c equal? What?
When the accumulation equals 0.
No. Where are we getting this plus c from? Where is it y plus c?
The y intercept.
So this is just an algebra question.
Negative f of a.
Negative f of a. That's what the c is. Negative f of a. Okay, and this f, this little f, is any antiderivative of the rate.
And it's only for improper integrals, correct?
What's for only for improper integrals?
Well, the f of x plus c. Like like say if it was 1x, then what would be my plus c? Like for the first example, where's plus c in that?
Here?
Yeah, that first example.
Yeah, you tell me. What's the plus c?
I'm assuming it's, oh well, actually it would be negative 1 to the 4th.
It'd be yes, opposite. So it'd be negative 1 if we use this as the antiderivative. So we use this as the antiderivative, and in that case, our plus c then is negative 1.
Not negative 1 to the 4th.
Well, I'm just simplifying to x to the 4th minus 1.
Oh yeah, well I'm saying like.
Well, that's confusing. Negative 1 to the 4th sounds like this, so that's why I didn't want to say that. That's confusing. It's not that. It's minus 1 to the 4th.
Yeah.
So it's
So like say if it was minus 3 to the 4th, then it would be minus 3 to the 4th. Like that would, the whole thing would be c, the minus 3 to the 4th.
that's right,
Yeah.
right there. Okay, so let's practice a little bit more here. Here's another one. So I want you to write, here's a rate function, 1 over 1 plus x squared. And I want you to write the accumulation function starting at x equals 1 in open form and in closed form. And you write the open form accumulation and the closed form accumulation starting at x equals 1. Anybody think they got the open form? Mackenzie, you think you got it?
Yeah, is it 1 to x?
1 to x.
Or, yeah, 1 to x, sorry. And then for the function, it's going to be 1 over 1 plus t squared dt.
1 divided by 1 plus t squared dt. What do you think? Is that it? Is that all you want? All right, let's graph that. There we go. And does it have a 0 at 1? Yes. Anybody think they got the closed form? Aaron, you think you got it?
I think I might switch this around on stage, but our tangent of x minus our tangent of 1.
So a tangent x minus a tan minus. So on your graphing calculator, the inverse sine and cosine and tangent, you write a tan or a sine or a cosine. Is that what you want? Brent, what do you think of that? How can we check? So before we graph it, we're not, instead of graphing it by now, we have a way algebraically of checking. So if we're not sure, what can we do? How can we check the closed form? And what should we get?
1 over 1 plus t squared.
Or x squared, right? Okay, so what's the derivative of arctangent x?
1 over 1 plus x squared.
And what's the derivative of arctangent of 1? How do we do? Is that the antiderivative of our original rate function? Got it. So here's the thing. How do we know how to get, here's the big conclusion. How do we know how to get closed form accumulation functions? How is it that we know how to get closed form accumulation functions? What's that? How is it that we knew that we looked at 1 over 1 plus x squared and we knew that the accumulation function was 1 over, the closed form was 1 over 1 plus x squared? How did we know that? Because we learned all the derivatives. We learned all the rate functions given the closed form accumulation. So it's not that we learn a whole new set of rules to get closed form rate from closed form accumulation from closed form rate. It's that we need to know all the rules of derivatives really well and be able to do them in reverse. Go backwards. So we're not learning a whole new set of rules to get closed form accumulation from rate. We have to be able to do antiderivatives or think about these rules in reverse. Go backwards. Okay, have a great break. Be safe. Have fun. Yes, we're turning the homework in.